Hello. I know what you've been thinking. We've got all these vector spaces lying around, norms. Be nice to have some linear transformations between them. Yes, I've got an answer for you. Operator theory. That's what we're going to learn right now. So, what, you ask? Thanks for asking, Peter. Is operator theory? Well, we normally have a couple of vector spaces. Let's call them x and y. Two vector spaces. We also call them linear spaces. And then let T from V to V be a linear transformation. This is also called a linear map or just a linear operator. Those are all words that mean the same thing. I think it's supposed to be cooler if you use operator. Anyway, well, so just to kind of give some examples, we're used to the ones from linear algebra where everything's finite dimensional, but there are lots of other ones where they're not finite dimensional. So, for example, if A is an n by k matrix, then T sub A from Rk to Rn defined by, I probably could have used complex numbers, but anyway, T sub A of x equals Ax is a linear operator. Yeah, and by the way, definition of linear transformation, who remembers that? Right, Shaylin. So anyway, for all these, it should be the case that scalars come out and then it respects addition. So you can say that for all alpha and beta in complex numbers, say, and v and w in x, if you take t of alpha v plus beta w, you get alpha t of v plus beta t of w. Yeah, so that must be the case for linear operators. That's really the only thing in the definition of a linear operator. So that's definitely true of matrices because of the properties of matrices. That's definitely true. All right, so what's some other examples? Well, suppose that that k of s and t is a function on, say, 0, 1 cross 0, 1. And say it's, a Lebesgue integrable bounded. Okay. Then for all f in C of AB, I'm going to say that TF of S is just, interval from 0 to 1. Yeah. Is defined to be the integral from 0 to 1 of k of st, f of t dt. So that is a linear map on the infinite dimensional space of functions. And if k is continuous, then t maps C of 0, 1 to itself. So let's just check linearity here. If you, for all alpha, beta in I didn't say it's complex valued, but let's say C, okay. And then let's say f and g and continuous functions on 0, 1. If you take t of alpha f plus beta g, you get the interval from 0 to 1 of k of st, alpha f of t plus beta g of t dt. And then by the properties of integrals, the alpha and beta come out. So guess what? It's the same thing as alpha tf of s plus, oh, and I should have put an s here, plus beta tg of s. Check. And so, in fact, there really is an operator, a linear operator. Right. And so just to give you another example, remember that little l2 is the set of all sequences an such that the summation of an squared is less than infinity, where an is in C. They're sequences of complex numbers. And yeah, you have to put absolute value then. Yep. Complex absolute value, right? And that's a set, and we know it's vector space, and it's a normed vector space even. So the left shift operator, when we call it S from L2 to L2, is defined by S of, I'm going to write out what the sequence is, equals, and you just shift all the numbers over 1 and you drop out the A1. So it turns out if this sum from n equals 1 to infinity converges, then also this one does, so it actually maps L2 to L2. And you can actually check it's a linear operator, because it satisfies the properties of a linear transformation. So good stuff. All right, so let's prove something. So here's a theorem. Yeah. Oh, so by the way, we're going to assume that our vector spaces are normed to linear spaces. So let x and y be normed linear spaces. What's that? Yeah, Lucas, that's kind of like a Banach space, but we don't assume that the normed linear space is complete. And so we don't say Banach space. Right. All right, so let's suppose we have normed linear spaces, and an operator t from x to y is continuous, this is what the theorem says, at every point if and only if it is continuous at a single point. Wow. So that's kind of an interesting thing. That's certainly not true in general. So let's do the proof of that. So we're going to actually, let's see, this direction is obvious because, you know, that is one special case of the first thing. So now let's look at this direction. So suppose t is continuous at x naught and x. So let's see. Yes, so that means for all epsilon greater than 0, there exists a delta greater than 0 such that absolute value of x minus x naught is less than delta, implies that the absolute value of t of x minus t of x naught is less than epsilon. Okay, I made a boo-boo on purpose. What did I do wrong? That's right, then these have to be norms. So notice x is a norm linear space and y is a norm linear space. So this norm is the norm on x. This norm is the norm on y. And now sometimes in books you put like a capital X here and a capital Y to make sure you distinguish between the two. And probably we should do that, but then it makes the notation really nasty. So I'm just going to I'll use the same symbol, but we just need to know where our points live. And then we'll know that, yeah, we're in the right space. Okay. So we now want to we want to show that it's actually continuous at any point. All right. So let's look at this. So suppose, so this is what we're given because it's continuous at x naught. Suppose v is another point of x. And w is in x such that the norm of v minus w is less than delta. Now, how can I relate this back to this? Well, I'm going to make it relate back to that. So then I'm going to take v minus w and then add and subtract x naught. So v minus w plus x naught minus x naught and absolute value is less than delta. Okay. Then, by what we've been given is the norm of t of v minus w plus x naught minus t of x naught is less than epsilon. But then we use linearity, and that tells us that t of v minus t of w plus t of x naught minus t of x naught is less than epsilon. That's right, Shaylin. Yeah, if we have any number of things added or subtracted, we can use the linearity property to separate them out like this. And notice we get that norm of t of v minus t of w is less than epsilon. So look, we just proved that t is continuous at v. QED. So we showed that if it's continuous at one point, it's continuous at any point. So it's great. And where this theorem is mainly used is then that means to prove that a linear operator is continuous, you only need to show that it's continuous at 0. That's usually the easiest point to check, because then, you know, x naught 0, so the formulas become simple. So anyway, so let's go ahead and talk about something else. So so that's that theorem. If x and y are nonlinear spaces, we say that an operator t from x to y is bounded if there exists an m greater than 0 such that the norm of tx is less or equal to m times the norm of x for all x and When this is the case, we can actually compute sort of the best possible m, and that's called the operator norm of t. When this happens, we let, and this is the norm of t, which is called the operator norm of t. It's the sup of over the norm x equals 1 of, and I could also put just x is not equal to 0. I just don't want to divide by something if it's 0. Of tx over x. And this is x in capital X. And so again, this top norm is the norm in y. The bottom norm is the norm in x. But because of this equation, tx over x, if x is not 0, is always bounded by m, so there really is a sup of it. And so that's kind of like the least upper bound of this over this, and that is called the operator norm. So for example, if M is an n by n matrix and T from Cn to Cn, we call it T sub m, is given by T sub m of x equals mx, then the operator norm of T sub m turns out to be, so it's the sup of T sub m x over norm x, where x is not equal to 0, and x is a vector in Cn, which, okay, so it equals the sup of mx over x. And then this is just the absolute, complex absolute value in this case. So this is actually kind of tricky to think about. Any ideas on this? You're right, Lucas, it does have to do with eigenvalues. Good. Yes, Shaylin, the maximum eigenvalue is a good idea. Yeah, in fact, it's the eigenvalue with the maximum absolute value. So it turns out is to be the maximum of the absolute value of lambda such that lambda is an eigenvalue of m. So that turns out to be what that is. And so if you can think of it, if x actually is an eigenvalue, you just get an absolute value of lambda popping out. And then you can write a basis of Cn in terms of eigenvalue vectors and generalized eigenvectors, and then with that information you can get that stuff. Anyway, so that's kind of an example. Let's see. So, for instance, so there's one example, and then another one. Like if we looked at the kernel example, if t of f is the integral of k of st f of t dt from 0 to 1, and t is a map from, so let's say this is continuous, and then t is a map from C of closed interval 0, 1 to itself, then it turns out that the operator norm of t in this case would be the maximum of this function. Overall t. 0. And then you yeah. And then overall and then you integrate that from 0 to 1 to be s. Oh yeah, no, it's the sup of overall s and t. I'm thinking L1. Yeah. So in s from 0 to 1. And probably have to put out some value. Yeah. Because you could, whatever the place this is the maximum, you could pick an example of a function that's just concentrated in that one point, and then that would give you kind of, when you computed this divided by the sup of the f, it would be similar to that. So, yeah. Well, it's definitely less than or equal to that. But so this is a bounded operator too. So both of these guys are bounded operators. Now, an important theorem is that t from x to y is continuous if and only t is bounded. So again, this is a linear transformation, a linear operator between normed linear spaces. So this is very interesting. So, boy, this certainly doesn't happen usually when you think of bounded functions and continuous functions and everything like that. But it does when you're talking about linear operators on vector spaces. So let's do the proof. So we are going to assume this direction. And let's do this direction. So suppose t is continuous. So for epsilon 1, we're going to choose that particular epsilon. Choose delta greater than 0 such that if I take the norm of x and make it less than delta, that implies that t of x is less than 1. Okay, again, this is the norm on x, this is the norm on y, and this is the showing, we're using the fact that it's continuous at 0. Then, for all x and x, if I take x tilde equal to delta times x, divided by norm x, and I'm going to divide by 2 also, the obvious choice, then norm x tilde is, let's just put that whole thing in there, delta x over 2 norm x. The constants come out because it's a norm. Delta's greater than 0, so that just comes out like that, over 2, and this is greater than equal to 0. Oh, and I should say x is not equal to 0. And then we have norm x, so this is delta over 2, and this is less than delta. Well, then that means that t of x tilde is less than 1. The norm, right? Because the x tilde now fits into that category. But then plug everything in, and you have t of delta x over 2x bar less than 1, and then pull out everything that you can using the linearity of t and then the norm. You get delta over 2 norm x times norm of tx is less than 1, which tells you that norm of t of x is less than 2 norm x over delta. So therefore, t is bounded. And see, this is true for all x and x is not 0. And by the way, this is definitely true if I put less than or equal to with x equals 0. And so we have that, and so the 2 over delta satisfies the m in the definition of a bounded operator. All right, so we proved that t is bounded, given that t is continuous. Now let's go the other way around. So suppose t from x to y is bounded. So before we proved, we were given it as continuous and we proved it was bounded. Then, for all x and x, norm of tx is less than or equal to m times norm of x. And yeah. So then, for all epsilon greater than 0, I'm going to let delta equal epsilon over m. Then, if I take absolute value of x less than delta, then the absolute value of tx is less than or equal to m norm x from that, but then that is less than m delta, which equals epsilon. So therefore, t is continuous at 0. But that means t is continuous from the previous theorem. Here we go. Pretty shocking, huh? Pretty amazing, yeah. All right, well, I did want to state another theorem. It's important. And I'm going to say, let B, curly B, and this is proper notation, x and y, those are two norm linear spaces, be the set of bounded operators from x to y. And this is a normed linear space if we use the operator norm. So we'll actually prove that and do a couple of exercises next. So see you around.